is Youngsoo Choi, and he's a computational math scientist in CASC at Lawrence Livermore. He's leading the data-driven reduced order model development team, and he has developed several open source codes, including libram and rum for Lagrangian hydrodynamics. He has an undergraduate degree in civil and environmental engineering from Cornell and a PhD degree in computational and mathematical engineering from Stanford. And prior to joining Lawrence Livermore in 2017, he was a postdoc at Sandia Labs and at Stanford University. And today, he's going to talk about his recent research on physics-constrained data-driven methods. Thank you for joining us, Youngsoo, and the floor is yours. Please go ahead.
Thank you. Thank you so much for the introduction and this opportunity to give the talk at PNNL. I heard that Mata told me that it's an informal seminar series, so I will try to be informal. So if you have any questions, please do not hesitate to interrupt me. Okay, today I would like to talk about several physics-constrained data-driven methods that can accurately accelerate computationally expensive physics simulations. I'm sure there are many experts in this field here at PNNL and Sandia, including George and Matar. Hopefully, what I'm presenting today is interesting enough so that we can collaborate to further improve this exciting field of research areas. I will take you through a short journey by starting with purely data-driven black box approach and gradually move toward the conclusion that why we need physics-constrained data-driven methods for physical simulations. I'm especially interested in developing efficient reduced order models yeah, okay. Of course, I couldn't have obtained all these results I'm presenting today by myself. I was fortunate enough to have awesome team members and many collaborators shown in this slide. I would not mention their names one by one, but they are just awesome to work with. Okay, now why reduced order models, right? You are looking at a beautiful simulation modeled by smooth particle hydrodynamics for shape charge penetration. The simulation is well matched with experiments, but very expensive. One fold simulation takes 7.4 days. This is unfortunate in the context of multi-query applications such as design optimization, uncertainty quantifications, where you need to do many different fold solves, exploring your parameter space. Therefore, many researchers have tried to build an efficient reduced order models that accelerate their simulations without losing much accuracy, right? And how you can build such a reduced order model by first considering a parameter space D. The parameter space can be initial condition, boundary condition, or material properties of shape charge simulation. Then you can collect data by solving a full order model with high performance computing machines for several sample points here and there. And then you apply machine learning techniques to build a reduced order models. Various machine learning techniques are available, so various reduced order model types are possible. But depending on how much you incorporate physics law in the reduced order models, it can be intrusive or non-intrusive. I will go over some advantages and disadvantages of intrusive and non-intrusive reduced order models, but once you build the reduced order model, you can accelerate simulations with and predict the solution at various query points here and there, and many more, which you have not seen in the training phase. So this is obvious that reduced order models are useful for the predictive science, right? Okay, these reduced order models can be categorized by its level of intrusiveness, as I mentioned. For example, black box approach, which is the least intrusive method requiring only data. Then we can think of a more intrusive method, which is the linear subspace reduced order model, so-called LS-ROM, where the state fields are represented by a compact linear subspace. An even more intrusive method that is nonlinear manifold, so-called NMROM, where the state fields are represented by a compact nonlinear manifold. Roughly speaking, more intrusiveness means more accuracy. So the intrusive reduced order models are more accurate than the black box reduced order models if the same amount of data are used, right? On the other hand, more intrusiveness means less speed up. So the black box method is faster than the intrusive methods in general. Also, the physics constraint reduced order models are more robust in extrapolation than the black box reduced order models, which will become handy in multi-query applications such as PDE constraint optimization, for example. Okay, let me try to introduce 3 different black box reduced order models. The first black box approach is the linear multi-step neural network. This method uses linear subspace dimension reduction approach, so-called proper orthogonal decomposition, POD, via singular value decomposition. To demonstrate that, let's say we have airfoil flow data denoted as W here, and we use POD or singular value decomposition to obtain a reduced basis for the solution variable. Then project the original airfoil flow data W onto the subspace spanned by the reduced basis phi and obtain the reduced data A. Then the linear multi-step neural network is trained using the reduced data A and the parameter mu in order to propagate in time in the reduced latent space. Then the full state is restored by the reduced basis phi. As you can see, we only use data throughout the whole process. So this is the black box reduced order models. By the way, this type of reduced order model is also called latent-based learning approach. The latent-based learning approach has 2 main ingredients. The first one is the compression, and the other one is the identification of the latent space dynamics. For example, this linear multi-step neural network method I have introduced here uses the linear compression using POD or SVD, and then linear multi-step neural network identification method for the latent space dynamic identification. Okay, we have applied this linear multi-step neural network based black box reduced order model for a steady flow around the airfoil simulations. Here we change the Mach number to compress data using singular value decomposition and train the linear multi-step neural network. As you can see, that the predicted reduced order model and full order model solutions are identical in eyeball norm, while the reduced order model takes only 2.55 seconds, while the full order model takes 314 seconds, giving us a speed up of greater than 100. Quantitatively, overall, in spatial domain, the relative error has a less than 1% error everywhere. Okay, another way of generating the reduced space or latent space is to use autoencoder. Let's say we have a porous media flow data. Encoder compresses the original data to a latent space, right? And then decoder decompresses the latent space data back to the full state. Because it went through the compression and decompression, the decompressed data is only approximated. So the autoencoder can be trained by minimizing the difference between this approximated data with the original data W. And then for the predictions, if the new parameter is queried, then various the interpolation techniques are used within the latent space. For example, the red-eye basis function or artificial neural network, etc. And this nonlinear compression technique is used and compared with the previous POD types of the compression technique for the porous media flow simulations. And we found that for the problems with Kolmogorov leaf decaying slowly, that is the one whose singular value decays slowly, the autoencoder approach outperforms the POD method in terms of accuracy. Okay, similar nonlinear compression approach is used in another method called a deep fluid, where the autoencoder is used for compression and decompression of the solution data W. Only difference now is that here the latent space dynamics are learned by the latent space time integrator after the autoencoder is trained. Since the size of the latent space is small, this time integrator it will be very fast, as you can imagine. Then with the predicted latent space solutions, we restore or reconstruct the full space by applying the trained decoder as usual. We have applied this deep fluid approach to the 2D Burgers equation problem, where the simulation is very advection dominated, Reynolds number of 10,000s, and the shock is formed and propagate to the rest of the computational domain, as you can see from the movie. The full order model and deep fluid solutions are very similar in eyeball norm, while the deep fluid gives a speed up of greater than 100, pretty good. However, the quantitatively deep fluid gives the maximum relative error of 38.6%. This might be good enough for animations or digital graphics, but it is a bit too large for scientific application. So for a better accuracy, we need to incorporate the existing first principle and the constraint, introduce those constraints in our model. Okay, one way of constraining, introducing the physics constraints in your reduced model is to use the projection-based reduced model. So here, in order to explain that, let's start with a governing equation represented by the ordinary differential equations. Here, W is a state variable, and F is a nonlinear function, and T is the time variable, and mu is the parameter. We first approximate the solution as a linear combination of reduced spaces V, whose dimension is a lot smaller than the full order model dimension. For example, like a singular value decomposition or proper orthogonal decomposition, you can obtain this V, right? And then you plug this solution representation into the governing equation. Then you will end up with overdetermined system because you have less number of unknowns than the number of equations. So in order to close the system, you apply some kind of projection technique. Here I have applied the Gallatin projection, and which gives you a reduced system of ODEs. Then you can apply your favorite time integrator to these reduced systems. For example, the backward Euler time integrator, just for the demonstration. This gives us the fully discretized reduced nonlinear system of equations. You have to solve in every time step. By the way, you have to treat the nonlinear terms here properly. Otherwise, the projection-based reduced model will be slower than the full order model. So people apply a hyper-reduction techniques where you sample and evaluate only important subset of the nonlinear terms to improve the efficiency. A most famous hyper-reduction technique is DEIM, stands for discrete empirical interpolation method. The DEIM introduces the nonlinear basis phi of F and then express the nonlinear terms as linear combination of nonlinear basis vectors. Then it introduces a sampling matrix Z, which selects or extracts an important subset of the nonlinear terms so that the action of Z on the nonlinear term F, only the subset of F will be evaluated. Now, the sampling indices of the matrix Z can be obtained through the various algorithms. DEIM and QDEIM are the popular ones. Then the generalized coordinate for nonlinear term F of hat can be obtained by solving the interpolation problem. Then you plug this expression into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with this somewhat crazy looking equations. But if you look at it close enough, a lot of terms can be pre-computed. And this nonlinear terms, which is changing every Newton time steps, it can be efficiently computed thanks to the sampling matrix Z in front of the nonlinear term F. This is how we achieve the efficiency through the reduced order models and the hyper reductions. There are many variants of the hyperreduction technique, the GNAT, ST-GNAT, NSNS, etc. There are many of them, but the main machinery or the philosophy of the hyperreduction follows more or less the same paradigm I just have introduced just now. Okay, this traditional, projection-based linear subspace reduced model can be used to accurately accelerate various physical simulations, achieving a speed up of 10 to 1,000 with a relative error less than 1% or 5%, for example. So, for example, this projection-based linear subspace reduced model has been successfully applied to several hydrodynamics problems. Here, you are looking at the cases where the reduced models achieves a speed up of 14.6 to 87.8, and with a indistinguishable accuracy level, that is a relative error around 0.1% or even less. So if you compare the full order model solutions and reduced model solution, and then with eyeball norm, you cannot distinguish the difference between those two. And one great thing about this projection-based reduced model is that its speed up will increase as we apply it to larger scale problems. Just to see that effect and demonstrate that we have refined the Rayleigh-Taylor instability problem and observed the speed up. As you can see from the graph, a higher speed up is achieved as the size of the problem is increases.
Sorry, can I ask a question? So for all these comparisons, when you talk about accuracy, can you explain how you're quantifying that? So is this like this is using your nonlinear autoencoder and so on. Is this evaluated on your training set?
Oh, yeah. Well, I'm going to get to the training set and the testing set together. But the problem, the results you have seen here is on the training set. We usually call it reproductive case, but right now I'm going to move on to the parametric case, the predictive case, or the testing case. A lot of
can you make a comment on the so for projective ROMs, right? Like usually handling hyperbolic problems is a challenge. Is that something you can comment on? Like, is there some technical details here?
That's exactly, here, this one is a hyperbolic problem. It's also advection dominated problem. This is well known that the traditional projection reduced linear space, subspace reduced model will struggle. So in order to obtain this type of accuracy and the speed up, we had to apply a special technique called the time windowing approach, where you dissect your time domain into several subdomains, and we build a local reduced model for each subdomain and concatenate to each other, so that each local reduced model has a small basis size, and also at the same time accurately represent the subspace solutions within that the time windowing. So this special type of the special treatment in the projection based linear subspace reduced model has to be applied to address this type of hyperbolic problem, as you mentioned, Nat. And later in the presentation, I will introduce other types of strategy to deal with these hyperbolic types of advection dominated problems.
Great, thank you.
Yeah. Okay.
Yeah, Youngsoo, the errors that we're looking at are the reconstruction errors, right?
Yeah, this is reconstruction errors. Yes.
Yeah. That's what I'm not asked before. Yeah.
Yeah, exactly. And then moving on to the testing error or the predictive error. Here is I'm going to talk about a robustness with the extrapolations. Okay. Unlike the black box approach, since the reduced order model directly incorporates the governing equation for the underlying physics, even though it is used to predict the solution for the parameter point away from the training data, it can still give a reasonable accuracy. That's what I mean by the extrapolation. For example, this graph shows the relative error of local reduced order models that is trained at the blast energy, initial blast energy at 0.25, right here, this base point. As the prediction point gets away from the training points, the accuracy of these local reduced models, which I have just built, deteriorates. But not much though. We still observe that a relative error of less than 1% is maintained around the blast energy of 0.1 to 0.4. For example, like this line represents the 1% error, and it meets here and there. If you go down and around these regions, this local reduced model, just which is built at 1 point, still gives you a relative error less than 1% around that base point 0.25. This has a great implication, by the way. For example, in gradient-based optimization, let's say you do not have sensitivity implementation. If you have some experience of the computing and implementing the gradient information from your PDE solve, you probably agree with me that it's very cumbersome and it's a lot of implementations, and still it's simulation time, the adjoint solve or the gradient computation time is very computationally expensive too. So by the way, if you use this robustness of this local reduced model, here you can approximate the gradient using the finite difference, and for each the function evaluations, you can use the reduced model because reduced model is accurate around these base points, right? So this is beneficial for the PD constraint optimization or design optimization, where the physical simulations is constrained. Another implication is that you can easily add more local ROMs to cover the broader parameter domains. But here, the question is how to optimally sample the local ROMs in your parameter space, right? And that can be done using the greedy algorithm. For example, this greedy algorithm tries to find a sub-optimal, if not optimal. Before this talk, I was trying to play this the movie, this problematic movie, set up ready, but it's not okay. It is what it is. Okay. Anyway, but this greedy algorithm tries to find a sub-optimal, if not optimal, set of the local reduced models whose overall accuracy is less than some desirable accuracy level, say, for example, 3%. As a demonstration, we set our parameter space to be a blast energy change from 0.075 to 1.25, just to show the different the behavior of the extreme cases. 0.075, although the movie is not playing, the shock is formed here. It does not hit the boundary and to finish the simulation. On the other hand, the simulation with the blast energy of 1.25, it hits the boundary and reflected it and interact with the incoming waves and do some more complicated things in blast energy 1.25. Okay, now the greedy algorithm starts by setting a desirable accuracy level. Let's say 3% relative error is desirable. Then build the first local reduced models in the middle, right? And then you compute the error indicator on the sampled points over the whole parameter space. The error indicator computation is cheap, so you can do that for many sample points. Then find out where the error indicator, the maximum error indicator occurs. This, denoted by this red point here. Then you build a local ROM there. Since you build a local ROM there, the error indicator will goes down around that area. And then find the next maximum points, which is denoted as this red points. And then you build a local ROM there. And you repeat this process until the overall the error indicator is less than 3% or etc. So we have actually applied greedy algorithm to the seed of blast problems and try to achieve the relative error less than 3%. And then the greedy algorithm spits out this 15 the points where the local reduced model has to be built. And with these 15 local reduced models, the overall relative error was less than 3% anywhere in this parameter space.
So this is one parameter, right? Just the blast time.
Yeah. As you increase the number of parameters, the greedy algorithm needs to run longer to pose.
Yeah, I cannot imagine that you can do that for 10 parameters.
10 parameters, yes. We have done for 8 parameters.
I mean, if you have the geometry, then the geometry you need 15, 20 control points.
Yeah, I totally agree. Yeah, so the maximum number of parameters we have used so far was the 8 parameters in the design optimization of the wing problem. Yeah, but as you said, increasing the number of parameters, you know, it suffers by the curse of the dimensionality. Okay, all right, enough for the projection-based linear subspace reduced models. If you are interested in knowing more about the details about the projection-based reduced models for Lagrangian hydrodynamics specifically, I would like to refer to this paper, which is under review for the publication right now. If you want to generate the numerical results that I have shown today, you can actually do that. Please download the following 2 software, Librem and Lagos, and then in order to help you with how to use those the softwares, we are actively developing a web page for the Librem, which is under construction. So I'm expecting to make it public either end of August or end of September. So please stay tuned. And then at the same time, we are also diligently making the YouTube tutorial video explaining how you use the data-driven the capabilities implemented in Librem and apply that to your own applications. So we are diligently making one by one, so please stay tuned for that. Okay, by the way, as Nat pointed out, if you don't apply any special technique, if you just apply just traditional the projection-based linear subspace reduced models, then it has a great limitations, and that is it cannot accurately represent a advection-dominated solution with a small basis size. That is the one with Kolmogorov with decaying very slowly. Let's look at the 2D burgers problem that you have seen before. As you remember, the solution is very advection dominated. As you can see from the movie, LS from shows fictitious oscillation in front of the shock wave if the reduced space dimension is 5 is used, resulting in a relative error of around 34%, which is not good enough for many scientific applications. The limitation of the linear subspace reduced models comes from the fact that the solution is represented by a linear combination of a fixed reduced basis, if you think about it. In order to address this issue, we are going to transition from linear subspace solution representation to nonlinear solution representation using nonlinear manifold reduced models. Okay, before I go into the nonlinear manifold reduced models, because you know, addressing this limitation of linear surface reduced model for advection dominated problem, it's so important that many researchers came up with their own solutions. For example, the shifted POD, proposal decomposition by Rowley and Rees, and the registration-based models by Tommaso Tadei in INRIA, and Radon transform the based reduced models and reduce the deep network by Donsov-Lee, and also the implicit feature tracking based method by Matt Jar, and the time windowing reduced models for Lagrangian hydrodynamics by our own folks, the Dylan Copeland. All these are available as a potential solutions. However, for the best of my knowledge, these 4 methods are still under development to be extended to the fully 3D problems. And this time windowing ROM requires many windows to handle a long time advection dominated problem. Not that it's not possible, I mean, but how about if without introducing all all those windows, is there a way of handling the advection dominate problem in another way, right? So now we are going to focus on the nonlinear manifold reduced models, which first introduced by Gukjin Lee and Kevin Carberg in 2020, by the way, where the linear subspace solution representation is replaced by the nonlinear manifold solution representation. Although they were able to obtain a great accuracy with a small size of latent space for the advection dominated problem, their method was slower than the full order model. It was making sense because they were introducing more nonlinearity in the model than the original the governing equations. So today I'm going to present a version of the nonlinear manifold reduced order models that is now a lot faster than the full order model simulations using hyperreduction. Okay, to formally explain the nonlinear manifold reduced models, here is the governing equations you have seen before, where W is your solution variable. We approximate the solution with the nonlinear manifold, which is represented by the nonlinear function G here. That maps a small latent space to the full order model dimension. The nonlinear map G is obtained through the autoencoder training with the solution data from the corresponding full order model simulations. Note that this decoder is mapping the latent space to the full order model state, so it is perfect for our nonlinear map function G. So we use the decoder as the nonlinear map function. Then we plug this solution representation into the governing equations, and as usual, we obtain the overdetermined system where you have more equations than unknowns. Here you must be careful with the nonlinear term. Again, as I emphasized before, we need to sample and compute only the subset of the nonlinear terms. Okay, so what kind of the projection is available to close the overdetermined systems? The first, the Galerkin projection is possible. Galerkin projection applies the projection first to obtain the reduced ordinary differential equations, then discretize in time to get fully discretized nonlinear system of equations. On the other hand, the least squares Petrov-Galerkin method discretize the time derivative first by applying some time integrator, for example, backward Euler time integrator. And then we close the fully discretized overdetermined system by taking the norm and minimizing it. Here, many crazy looking terms appear as before, but that can be pre-computed. And also this sampling matrix Z through the hyperreduction is key to accomplishing efficiency, where you only compute a subset of the nonlinear terms, not all of them. But now, since we have introduced the neural network into the picture, the structure of the neural network in the decoder is very important. So in order to go over that, let's first look at the neural network with the two hidden layers as a decoder. Let's say that this orange disk in the output nodes are the selected ones by the sampling matrix Z in hyperreduction. You will notice that the many hidden nodes are connected, and as you go deeper and deeper in the hidden layers, the number of connected hidden nodes are increasing very fast. And this actually degenerates the efficiency of the nonlinear manifold reduced models, especially in the step of computing the Jacobian of the neural network. On the other hand, if you use a shallow neural network that is one hidden layer only, and if you sparsify it, and output nodes here is very small, right? So that the Jacobian computation of the neural network, it can be efficiently done, and ultimately it gives you the efficiency we need in the nonlinear manifold reduced order models. Okay, so here we compare the performance of all the reduced order models that I have introduced in these presentations, including the nonlinear manifold reduced order models, PNNL, linear subspace reduced model, LSROM, and the black box approach, deep fluid. As you can see from the movie, PNNL and full order model are almost identical in eyeball norm. Not just eyeball norms. Quantitatively, PNNL achieves less than 1% maximum relative error. Furthermore, a speed up of 11 is achieved by the PNNL. Okay. Another potential way of overcoming the issue caused by the advection-dominated problems is to use the space-time reduced models. This work was done by very many people: Kevin, Peter, Bob, Kevin, another Kevin, Youngsoo, and Karen Wang. The space-time reduced model tries to reduce not only the spatial degrees of freedom, but also the temporal degrees of freedom. It does that by introducing both space and time reduced bases, denoted as psi and phi here. And then you combine those two bases through the Kronecker product to represent the whole space-time solution degrees of freedom with this the temporal and spatial the basis. Then the coefficient in front of this basis, space-time basis, will become your new unknowns, right? New coordinates. So therefore, it is obvious that it maximally reduces the total number of unknowns, because this reduces not only space but also the time domain. Okay, and then the solution, the space-time solution representation is plugged into the space-time formulation as usual, and then form an overdetermined system. Now you are hearing this like 3 times in this talk again already. This overdetermined system is closed by taking the norm of the space-time residual and minimizing it. And again, we apply the weighting matrix. This is a Z in space-time, like the sampling matrix, for the hyperreduction to achieve the efficiency for the nonlinear dynamical problems. Okay, we have applied the space-time reduced model to a large-scale particle transport problem, whose problem size is around 10 billion degrees of freedom in space and time. We were able to reduce those 10 billion degrees of freedom to only 10, and still gets the pretty much the same physics response as shown in the movie. The full order model took 17.4 seconds with 256 cores, which is not bad. But the space-time reduced model further reduces the computational cost to using only 1 core. It takes 0.006 seconds, which gives us a world time speed of around 2,900 or 700, something like that. And then quantitatively, the relative error is less than 1% throughout the time series. By the way, this was also again, the reproductive case. For the predictive case, I don't have a slide for that, but for the predictive case, also the local space-time reduced model was able to extrapolate pretty well for the perturbation of the parameter, and still gets pretty good accuracy there. I should have included one slide, dedicated slide for that, maybe next time. Okay. All right. The last topic today I would like to share is the component-wise reduced model lattice design algorithm. This is not particularly a method of handling the advection-dominated problems, but it is a nice way of overcoming an issue of a distributed parameter space, which is mentioned by George in the talk before, like dealing with the distributed parameter space whose dimension is like the scales with the full model discretization, like becomes million, billions, etc. So although I will demonstrate the capability with the design optimization context, but I do think that this will be great interest to you all for your own applications. Okay, this work is done and being done, currently being done with Sean McBain and Karen Wilcox in UT Austin. And just to give you a motivation for it, despite all the successful stories of the reduced models that I have shown so far, as the full order model size increases, the cost of training becomes very expensive and sometimes not even possible, maybe because of the memory issues. Also, if the parameter is spatially distributed, that is often the case in topology optimization problems, the dimension of the parameter space becomes too high to be tractable. Therefore, we looked for an alternative approach and found the component-wise reduced model, so-called CWROM, pioneered by Professor Patera's group at MIT. The method deals with a small size of data, so the training cost is greatly reduced. Each small reduced to the model components can be assembled like a Lego block to form a system reduced to the model. This is ideal for multi-components and multi-physics and domain decomposition simulations. Among many potential applications, useful applications of component-wise reducible models, I would like to focus on the microstructure design or metamaterial design, which is a great interest these days because of the advance in the 3D printing. There are many microstructures found in nature, for example, oyster shells, bone, honeycomb, and cactus lattice, etc. All these are there because they can achieve the maximum strength with lightweight. So many industries, labs, and universities are trying to mimic these attractive features of the metamaterials by solving for an optimal lattice structure design problems. To model the microstructure or lattice structure, by the way, it would be the most accurate if you use a monolithic finite element method with very high resolution. Unfortunately, this is computationally very expensive. This hinders a fast fold calculations, which we would need many of them in design optimization context to explore the parameter space. So the people came up with all sorts of approximation, the surrogate alternatives. For example, homogenization-based design, where it homogenizes a given the unit cell and fill the computational domain with the homogenized unit cell. Then you solve a continuum topology optimization with each unit cell being represented by a finite element. Then the problem, but however, the problem with this method is first, it assumes infinite periodic boundary conditions. So it is very inaccurate on the external surface. Second, the model is not valid when the unit cell size is comparable to the system length scale. Third, the optimal design has uniform pattern space filling structure, which is bad for the design of functionally graded the materials. Therefore, we need much better accurate algorithms than the homogenization-based method. Alternatively, one can model each lattice component with beam elements, right? Then through the design optimization process, one can get rid of unnecessary beam components to minimize the weights and maintain the necessary the strength with minimum weights. Here is a picture of the 3D printed design. You can manufacture using the 3D printing. Although this beam element based approach has many advantages, such as being simple and fast, enable system level design and the functionally graded design also, it has a major problem of inaccuracy again, because the beam theory assumes that it's gotta have the length scale, much larger than the cross-sectional length scale, and the accurate stress value at the joint is not available. So what we need is more accurate and also at the same time the fast computation method for lattice structure design. So we had, as I mentioned, the component-wise reduced model was the way to go. And in order to explain the process of the component-wise reduced model and how, and I'm going to explain how I incorporate that in design optimization. First of all, we identify the reference components. Here we have identified the simple joint and the strut component geometry. Then you introduce finite element discretization for each reference components. Then we build component ROMs for each component, that is joint ROM and the strut ROM. Within this process of building component ROMs, we have to introduce very important concept called the ports, which is an interface that talks to environment. For example, it connects with other components ROM, and also it can be used to impose boundary condition. Of course, you can add more components through unavailable ports. Also, it can be used to apply external force, and you can even rotate the component and attach to the system, and attach many more as you wish to form your desirable system domain. Then in design optimization, we assign a density variable to each component, which varies from 0 to 1. Usually we avoid 0 to ensure the well-posedness. So we set our low bounds to be 0.01. A small density variable implies putting no material there. And density of 1 means you put the material there. We automatize this process by solving a design optimization where the density variable becomes design variables and minimizing the constraints using the weight constraints, etc., to find an optimal lattice structure, for example, to minimize the compliance of the system. Here is a numerical example for lattice structure design using component-wise reduced model. Here we minimize compliance, imposing a constraint of mass being at most 40%. The downward pressure force is applied on the top, and Dirichlet boundary condition is applied on the bottom. And the full order monolithic finite element solve involves 2.7 million degrees of freedom, while the CW-ROM has only about 4,000 degrees of freedom. We apply the optimization solver called the MMA, which is very popular in design, solving a density-based topology optimization. The movie, yes, it is playing, right? The movie shows the optimization history from the beginning. Initially, it started with a uniform density variable and evolves into an optimal design, where the blue component implies no material there, while the red component implies density variable of 1, so you put the material there. So the red is the optimal design, the lattice structure design we end up getting using this design optimization process. Okay, here is the computational cost comparison. We have increased the port dimension from 8 to 62. The total degrees of freedom in the port was 62. So if we set the port dimension to be 62, then it's the same as the CW, the same as the full order model. So we compared our CW-ROM with the monolithic finite elements, and as we increase the ports, the expensiveness increases, right? And when we compare this, the port basis number of 8 with the monolithic finite element, we get 660 speedups, and compare with the CW-FOM, which is the component-wise version of the full order model, we get the 70 times speed up. And how about the accuracy? The accuracy is also great. The smallest CW-ROM achieves a relative error less than 1% already with respect to the full order model solutions. And the CW-ROM accuracy can be tuned. That's well-known fact. As we increase the port basis dimension, the accuracy improves, exponentially, as you can see from here. Okay, currently we are extending this component-wise reduced model approach to a stress-constrained lattice structure design problem where the mass is minimized with stress constraints. This is considered to be a harder problem than the minimizing the compliance problem. Here we introduced 4 different components. Then we defined a computational domain as demonstrations. We used L bracket, which is a typical the stress constraint problem, benchmark problem. Then you assemble and fill the computational domain with 4 component ROMs, and then delete unnecessary components to find out the optimal L bracket lattice structure. Here is the zoomed in picture of components in optimal design. And here is the corresponding very detailed stress control plots, which you cannot get with other types of lattice structure design methods, such as homogenization or beam-based methods. Okay, now let me conclude the talk with some summary. I hope I have introduced many interesting reduced order model techniques, physics constraints, data-driven approaches. The examples I have shown you include the non-intrusive reduced models for airfoil and another black box approach, deep fluid on 2D burgers creations, and the time windowing the reduced order models for Lagrangian hydrodynamics problem, seed of blast problem, and the space-time reduced models that achieves around 2,700 speed up for large-scale transport problems. And then component-wise reduced models for lattice structure design, and then nonlinear manifold reduced models that finally achieves a speed up with a great accuracy for direction-dominated problems. I hope that the reduced models works presented today is interesting enough to encourage future collaborations. With that, let me conclude my talk here, and thank you so much for listening.
Thank you, Youngsoo.
Thank you. Thank you.
Do you have any more questions from the audience? I wanted to ask you actually, in everything you have presented, you have to make several choices along the way, like the dimension of the latent space, and then at some point you showed like hidden layers, and you said, you know, we can select the number of layers, the number of nodes. How did you make those choices in your experiment?
That's easy to make for the traditional linear subspace reduced model, because when in the compression steps, like for example in singular value decompositions, you can observe the singular value decays, and you will know more or less, you know, if you truncate this much, then you will get this sort of the accuracy in your models. You have a better idea with the linear subspace reduced models. However, the nonlinear manifolds, you know, the compression techniques such as the autoencoder, etc. It's kind of hard to know ahead of time what sort of accuracy you will get. So the approach we have taken so far is just start with a small latent space and then gradually increase. And on top of that, there are so many hyper-tuning parameters in neural network training, right? So which makes the training itself is very challenging. Yeah. So there are pros and cons in linear subspace reduced model and nonlinear manifold reduced models. And the training is especially challenging for the nonlinear manifold reduced models, just like other types of neural network based models.
Yeah, sure.
Can I ask a question about the topology optimization?
Yeah, sure.
Do you mind just sharing some more details about it? I'm curious how you, how these things connect to each other, how you set up the optimization problem and how you explore. There's a lot of like combinatorial choices. So, right. So for example, each, I forget what you call it, each block connects through a port.
Right.
And an optimization problem that leads to an interface condition and all these kind of things. Can you comment on how that optimization problem is set up? So
okay. So for the setup of the design optimization, for example, here the mu here is the density variable, which each density variable is assigned to each component, right? Oops. Each component. Okay, let me write. Each component, right? And the density variable varies from 0 to 1, and 0 means you don't put the material there, and 1 means you keep the material there. And we automatize, you know, those those decisions by solving the design optimization, where the mu becomes design variable, and of course you must have your some sort of quantity of interest you would like to minimize, or the constraints. So for this particular problem, we try to minimize the compliance and subject to some mass constraints. It means that minimizing the compliance means the maximizing the stiffness of the overall the structure. And then please, we are asking the design optimization to please achieve that with these constraints being like the mass being, you know, the less than the maximum mass specified this upper bounds. And by solving this design optimization, of course, in order to solve this optimization, we had to find the gradient of this compliance with respect to the density variable, and which was able to be done in component level. So once you worked out those gradient or sensitivity analysis within the component level, we were able to directly apply that to this design optimization to solve that using the gradient-based optimizations, because with this high dimensional parameter space or design variables, without using the gradient-based optimization, there's no way you can find the solution in reasonable time. So we had to implement the sensitivity in component levels, and then use that to solve these design optimizations. Yeah. So I don't know. Maybe you need more details, but I guess I can refer that to this paper, the component-wise reduced model lattice type structure design, which is just published in CMAME.
Oh, that's perfect. Thank you.
Youngsoo, I have a question on actually one and a half question. The half question is the data that you show for the SPH. That's a very nice simulation you show in the very beginning.
Yeah, smooth particle.
Is it the SPH? Was it just one simulation? Because you implied that you actually had a parameter space, or it was just to tease us? Yeah, do you have a lot of simulations like that?
Well, this one is for just one simulation. I mean, okay, is it plain?
I'm just interested in the database, actually. Is there a database, or is it just one simulation?
Yeah, this is just one simulation, and we haven't constructed a reduced model for this SPH model yet. We would like to, but we haven't got the chance of working with this data yet. I mean, this will be challenging because just generating the data itself will take a long time. Look at this, just one-fold simulation.
Right, that's why I asked. But I'm interested in the data. I'm not interested in the reduced order model. I'm interested in the data.
Yeah. So
but
yeah,
this is only one.
Yeah, this is just a one-fold simulation.
One simulation. Yeah. Okay.
Yeah, I mean, the goal of the simulation was to try to match the experimental data. As you can see here, they have experiments, and then they have all the parameter sets, fixed. So they were interested in as accurately as possible, mimicking those experimental data, experiments results with the simulation data. That was the goal of this.
Okay. And now my question, that was my half question. My full question is not exactly philosophical, but it's a kind of approach question, which is learning. I mean, for example, you show that you use neural networks here, but do we actually, there's no learning involved, right? Because learning, by definition, learning, and that's the difference from optimization, is that you have many more parameters. You have an over-parameterized network, and therefore you use regularization, and regularization, if done properly, allows you to learn and generalize.
Yeah, I know exactly what you were talking about.
But you are in the under-parameterized regime, severely under-parameterized, which certainly, I mean, you show us this V shape, which is fine, but I mean, it's really a matter of philosophy. The modern era of learning is, I mean, of this type of even surrogate models, is that you actually go to hugely over-parameterized networks. So if you go to under-parameterized, of course, you do projections and they work well for the linear models and so on, but then we know all the issues with generalization. So my question is, and it's not a question to you, just to the community of reduced order modeling. How do you bring learning into ROM? Because it's not truly learning. That's my point.
Yeah. So physics informed neural network in your pins, the learning is, the learning the PDE, right? Learning the governing equations. In the reduced model context, I would say the learning is learning the subspace. of the solution, solution lies. The solution subspace where each simulation solution lies. So by identifying or the learning those subspace, hopefully that subspace has a small dimension, so that once that subspace is identified and learned, we can use that into the reduced total models, so that we only solve for small number of unknowns instead of the million or billions. And then the goal of the reduced model, I don't know, philosophically, is there is a underlying, corresponding, the full order model, discretized, highly resolved the solutions out there. That's why we use those data. And then with the reduced model, we try to predict and achieve a same level of fidelity for the new points using those subspace we learned through the reduced model construction process. So I would phrase that way the concept of learning in reduced model.
But it's not learning; it's training. The difference between training and learning. If you look at the information bottleneck theory, what I think the ROM is a training, and of course, in neural networks we also do the training. But if you follow the information bottleneck theory, Naftali Chisby, who just passed away, unfortunately, he shows this nice plot, which has the gradient of the weights, for example, right? And if you look at the training period, the mean value of the gradients of the weights is large. Then when the real learning period starts, which is what he calls the diffusion period, the fluctuations of the gradients of the weights are larger than the mean of the gradients of the weights. What does that mean? It means that the gradient descent, stochastic gradient descent, allows you now during the learning period beyond training. That's why he says always go 10 times more beyond that. And then because of these fluctuations, you now explore a much bigger space. That's why the over-parameterization comes in. In the reduced order modeling, you are in the neighborhood. You have no chance. So you're trained to know exactly the neighborhood, nothing else. You have no chance to actually generalize. That's my point. It applies to all under-parameterized and also, of course, determined, precisely determined systems. But that's actually the worst. Underdetermined is better than just precisely. But that's the point. There's no actually learning component. That's something that I think people confuse.
Yeah. Well,
you learn this. You learn your space, as you said well, but that's not learning. It's not true learning.
Yeah, exactly. I mean, in the context of transfer learning, I do think that this component-wise reduced model has that flavor a little bit, because the training is done in each component level, right? And then true learning can be done by assembling these components all together in different ways to form a new problem, and then find out the new solution which you never seen before. So that's right. That's right. True learning. So yeah. So I mean, there's in component-wise reduced model, that learning concept is there. But yeah, as you said, the other types of just spatial reduced models and space-time reduced model, I guess it's just a training. Yeah.
Well, I guess if there are no more questions, we can thank Youngsoo for joining us today. Thanks a lot for your talk.
Thank you so much. It was a great experience. Let's keep in touch.